Line integrals, part 3. We're going to start off with a short summary. C is a smooth-oriented curve parameterized by arc length, and at every point of C, the unit tangent vector points in the forward or positive direction of C. Let F be a vector field that is continuous on the curve. To add up the components of F in the direction of T at each point on the curve, we integrate f dot t over the curve. If C is parameterized by t, then we can use r prime. A common application of line integrals using the tangential component is computing the work done in moving an object in a force field, such as a gravitational or electrical field. In part 2, we found the work done in moving an object within an inverse square force field. Another application of the line integral is in studying circulation. Circulation of a vector field along the closed curve is a measure of how much of the vector field points in the direction of the curve. As you travel along the curve in the forward direction, how often is the vector field at your back and how often is it in your face? Circulation is the sum of the components of F in the direction of t for each point on C. We find circulation by finding the integral of the dot product integrated over C. And we can still use the same formula if we parameterize with t. So let C be the unit circle with counterclockwise orientation. Let's find the circulation on C for the following vector fields: the radial vector field xy and the rotation vector field negative yx. We will start by parameterizing the curve. Keep in mind it's a unit circle centered at 0, 0 with counterclockwise orientation. And easy parameterization for that is just cosine t sine t. And we're going to need r prime, so we go ahead and find that. The radial vector field on the parameterized curve is just cosine t sine t. Since the dot product is 0, the circulation is 0. And the radial vector field, as you can see, is orthogonal to the curve. So for each point on C, the component of F, the radial vector field pointing outwards in the direction of t, which points in the direction of the curve, is 0. So it makes sense that the circulation is 0. Let's look at the rotation vector field. At each point on the curve, the dot product f dot r prime is equal to 1, giving a positive value. At each point on C, the rotation vector field is tangent to the curve, pointing in the same way as the curve. And so the circulation is positive. So in summary, for the radial vector field xy, that is orthogonal to the tangent vectors of C, giving a circulation of 0. The rotation vector field negative yx is in the direction of the tangent vectors of this curve, and the result is a positive circulation on the curve. As already stated, the line integral of a vector field involves a specific component of the vector field relative to the oriented curve. We've been talking about the tangential component, and we defined both work and circulation. Suppose we would like to find flux, the sum of the components of F which are orthogonal to the curve. So if n is a unit vector normal to the curve, then the component of F normal to the curve would just be f dot n. Since flux is the sum of the components of F which are orthogonal to C, in order to find flux we calculate the line integral. As before, We need to be able to find flux when the curve is not parameterized by arc length. If C is parameterized by T and the vector field F is equal to, its components are the functions F and G, then to find flux, we first find F times dy dt minus G times dx dt. And then we just integrate that from A to B. Now, flux, this definition of flux, assumes a closed curve with counterclockwise orientation. If F points outward on a curve with counterclockwise orientation, then the dot product is going to be positive, giving a positive contribution to flux. If F points inward on the curve, then the dot product will be negative, giving a negative contribution to flux. Let's go back to our unit circle and find the flux across the curve for both the radial and rotation vector fields. The curve is parameterized with t, with cosine t, sine t. And rather than finding r prime, we're instead going to write it slightly different. We're going to find dx dt and dy dt because the formula just looks a little bit different. So we find dx dt, and then we write f in terms of t, and then we need to find f times dy dt minus g times dx dt. And in this case it's equal to 1. Then I add up the components of f in the direction of n for each component on the curve. Since the integrand is equal to 1, then I get a value of 2 pi, positive. This positive outward flux is consistent with the observation that the radial vector field points outward across the curve and that C has counterclockwise direction. The rotation vector field on C, let's look at that. Again, dx dt and dy dt, we have to find that. And then we need to find f times dy dt minus g times dx dt. In this case, it's equal to 0. And since we get 0, the components of f in the direction of n for each point on C is 0, giving a 0 flux. Because the rotation field is orthogonal to n at all points of C, the outward flux is 0. So, radial vector field xy has outward flux of 2 pi and 0 circulation. The rotation vector field negative yx has 0 outward flux and a circulation of 2 pi. Take care, and I'll see you in 15.3.